Very often, in the real world, when we have to solve decision-making problems, we have little or no knowledge of environmental dynamics. In other cases, even if we have good state transition models, when the number of state and actions is too large, we cannot solve these problems by means of exact methods such as dynamic programming. In all these cases, we can use reinforcement learning techniques, which are able to learn the solution by directly interacting with the environment or with the simulator. In reinforcement learning, the knowledge of the transition model is replaced by observing the effect of the action on the environment. We call experience sample a sequence composed of state, action, next state, and reward. Reinforcement learning techniques can be classified along several dimensions. One important distinction is between model-free and model-based approaches. In both cases, we do not assume to have prior knowledge of the transition model. In model-free approaches, we aim to learn the optimal policies by directly evaluating their performance. In model-based approaches, instead, we observe the interaction between the agent and the environment in order to estimate a model of environmental dynamics. Then, we apply an exact approach to this model. Model-free approaches are more computationally efficient than model-based ones, and they do not require us to specify a parametric model to be estimated. On the other hand, model-based methods are usually more sample efficient. That is, they can learn with fewer experience samples. But they may fail to learn the optimal policy if the considered parametric model is not adequate to represent the environment dynamics. Another important dimension for the classification of reinforcement learning techniques is related to what the method estimates. Along this dimension, we have three main categories: value-based, policy-based, actor-critic. Value-based methods use experience samples to directly learn the optimal value function. These methods take inspiration from dynamic programming algorithms and replace the expected values contained in the Bellman equation with a sampling variant that considers only the action chosen by the agent and the next state reached. In particular, Q-learning, one of the most popular reinforcement learning algorithms, is a model-free value-based method that is inspired by the value iteration algorithm. After performing action A in state S, Q-learning updates the value associated to the state-action pair SA, using the immediate collected reward and the value associated with the best estimated action in the next state. Q-learning is guaranteed to converge to the optimal value function under the assumption that each state-action pair is visited infinitely often, and that the learning rate alpha is decreased to 0 according to a proper decay schedule. Value-based methods usually perform well in Markov decision processes, while they struggle in decision problems characterized by partial observability or with very large action spaces. In 2013, Q-learning was combined with deep learning techniques, giving birth to the Deep QNetor algorithm, DQN for short. In DQN, the value function is approximated using a convolutional neural network, which allows the algorithm to learn in decision-making problem with an extremely large number of states. Originally, DQN was used to train agents to play 57 Atari games directly from pixel input, achieving human-level performance in most games. Since then, DQN has been improved in many ways. Now we have deep reinforcement learning algorithms that reach or even exceed the human level across all 57 games. The second category for the classification of reinforcement learning techniques is the policy-based methods. Here, the idea is to define a space of parametric policies and then search for the parameter that achieves the best performance. The most popular algorithms in this category are the policy gradient methods, such as reinforce and GPOM-DP. Starting from an initial policy gradient methods perform a gradient ascent optimization over the policy parameters, where the gradient direction is estimated through trajectories generated by the execution of the current policy in the environment. Policy-based methods allow us to deal with decision-making problems characterized by high-dimensional and continuous state action spaces. Furthermore, compared to value-based methods, they are less sensitive to violation of the Markov assumption and can learn good solutions even in partially observable problems. For these reasons, they are often employed in robotic applications. In addition, they can allow us to learn stochastic policies, which can be useful in decision problems in which multiple agents interact. On the other hand, they require a lot of data to estimate direction for improvement, and in general, they may converge to a local optimum rather than a global one. The third category of methods tries to combine the strong points of the previous two. In actor-critic method, there are two main components: the critic, whose goal is to estimate the value function of the current policy, the actor, whose goal is to implement the agent policy and update it according to the suggestion coming from the critic. In this way, actor-critic method can enjoy the sample efficiency of value-based method, as well as the ability to operate in high-dimensional continuous control problems, such as policy-based one. Popular actor-critic algorithms are A2C, TRPO, PPO, and DDPG. Reinforcement learning research is growing quickly and in many directions. One of the central problems is finding the right balance between exploration and exploitation. Indeed, we need to explore in order to understand the effects of our action, but at the same time we want to reduce our exploration as our knowledge becomes more reliable. Finding the best way to move from exploration to exploitation is paramount for the success of reinforcement learning algorithms.